Welcome back everyone. In this lecture we will continue with the representation theory. So, let us actually give some examples of representations. So, again I will work with general associative algebras. So, then slowly we will move to finite group representation theory. So, recall. So, we will start with A being an associative algebra with unity. So, we can actually produce lots of interesting representations using the old representations. But anyway, let's start with something very basic. So, we can actually take only the 0 space and make this into representation by defining A dot 0 to be 0 for all A and E. So, this is what called trivial representation. So, sometimes one dimensional representation is also called trivial based on maybe let us not. So, we just call this as 0 representation, let us not confuse, let us call it 0 representation of capital A. So, the most important representation of general associative algebras is the regular representation. So, we can take V to be A itself and then we can make A to act on A via left multiplication. You define this row regular, which is a map from A to endomorphism of A. So, where A goes to this LA, which is a map from A to A, which sends B to AB. So, it is a left multiplication, and one can check that this defines indeed representation of capital A, and this is called regular representation of capital A. So, we already seen that how to actually get new representations from old representation by taking subrepresentations, direct sums and so on, and quotients. So, let me first actually give you something very concrete. Okay. So, here for example, we can take A to be the polynomial algebra generated by let us say n variables. So, now to construct a representation of capital A, all we need to do is we can take some n number of mutually commuting operators from endomorphism of V, and then we can just assign xi to those commuting operators. So, let us fix T1 etcetera Tn from endomorphism of V, assume that they mutually commute. So, then what we can do, we can define this xi goes to Ti for all I between 1 to n. So, this is a map from A to endomorphism of V. So, this is again we can call it as evaluation at T1 etcetera Tn. So, this is indeed a algebra map, and so this xi acting as Ti gives us representation. So, this is an example of representation. So, when n equal to 1, so we were actually dealing with that representation of Cx. So, we will see more representations actually, and very explicit examples when we specifically work with group algebras. Okay. So, maybe I will do that later. So, now what I want to do, like some of the terminologies that I defined earlier, okay, I want to actually explain like what they corresponds to in the representations of Cx. So, we already seen that the indecomposable corresponds to indecomposable cyclic T invariant subspace, but one can ask that what is actually cyclic T invariant subspace, whether that is natural thing in representation side or not. So, that is indeed true. So, what one can do, actually one can talk about subrepresentation generated by a subset. So, like we did it in the T invariant subspaces. Okay, maybe let me define that. So, we fix this representation of capital A, and so we fix a subset S of V. We want to talk about subrepresentation generated by this S. So, we denoted by this. So, this is what we call the subrepresentation of V generated by capital S. So, this is by definition we just simply take all possible intersection of subrepresentations of V that contains S. So, basically take all W where W is subrepresentation of V and then S is contained in W, and it is easy exercise that this is indeed subrepresentation. And it is easy to prove that it is the smallest representation containing S. So, with respect to the inclusion. So, basically the subrepresentation of V generated by S exists. So, now how one can interpret in terms of the action of capital A. So, let us see an example. So, let us start with S being just a single vector V. So, then the subrepresentation generated by this V is going to be just intersection of all possible subrepresentation containing V. In particularly, it should have all elements A V, A in A. And if you think about it, the right hand side set all possibles A V, A in A, that is going to be subrepresentation. So, this subrepresentation generated by V must be equal to this. Usually, we denote this by just A V. So, if we use this notation, then it is clear that for any set, so now for any set S of V, the subrepresentation generated by S is going to be just sum of all possible this A V V in S. So, when I write like this, so this actually only means the finite sums. So, this is exactly equal to you write A 1 V 1 plus etcetera plus A n V n, where A s comes from capital A and V s comes from capital S. So, this is one way of expressing this subrepresentation generated by S. So, now if you go back to the cyclic subspace which is T invariant. So, you can see that when A equal to C x, so this Z T x, sorry T v, so this is going to be span of all the vectors V, T v, T square v and so on. So, basically this is exactly you take any element of C t, apply it on V. So, that means this is just C x applied on V. So, the subrepresentation generated by single vector V is nothing but the cyclic space. So, now let us recall the important notion called irreducibility. So, irreducible representations are the representation that has only 0 and itself as subrepresentations. Now, when A equal to C x, so we already seen that any finite dimensional representation has this Jordan normal form. So, let us say V is finite dimensional representation of this capital A. So, then V you can write it as V1 direct sum etcetera direct sum VR, and this each Vi is indeed isomorphic to V lambda I comma Ni. So, this is the Jordan block. So, then we have a basis of this Jordan block. So, with respect to that basis, so with respect to this, so if we write this the action of x restricted to Vi. So, with respect to this basis Bi, you can see this looks like lambda on the diagonal and 1 on the first half diagonal, 0 is elsewhere. So, now this first column, so that is indeed something very interesting. So, you can see that there is this vector. So, let us call it corresponding to E1i. So, this x applied on E1i is going to be exactly equal to lambda E1i. So, that means this column corresponds to an eigenvector corresponding to the eigenvalue lambda. So, that means this subspace C1i, so this is invariant subspace. So, it is indeed subrepresentation of this Cx. Okay. Since this is one dimensional representation, so this must be indeed irreducible representation. But you can already see that. So, this also implies any irreducible representation must be one dimensional, but anyway that you can take it as exercise. But from this observation we conclude that irreducible representations of this capital V, they corresponds to this very first columns of these Jordan blocks. So, we can write this x in terms of the Jordan blocks. So, where we have this matrix of x with respect to some basis B, such that j lambda 1 comma n 1 and so on, j lambda r n r. So, now each individual block exactly looks like this. In that block, if we take this first column, then that corresponds to irreducible module of V. Okay. So, let me just prove the fact that I actually told you now. So, if we actually consider this Cx representations, then it is indeed true that any finite dimensional irreducible representation of Cx must be one dimensional. Indeed, this fact is true even for general commutative associative algebras. So, to prove that, so first let us actually recall the Schur's lemma, which is a very important result, but the proof of this lemma is somewhat very easy, but this is actually very much used in representation theory. So, let me just state the result. Again we can assume A to be general associative algebra. So, let us take V W to be representations of capital A. Let us assume they are all defined over complex numbers. So, now let us say we have a homomorphism of representation from V to W. So, this is homomorphism of representations. So, now if we assume that V is irreducible, so then we can conclude something about the map pi. So, if V is irreducible, so then that implies this pi is indeed injective map. the second property. Similarly, if we assume something about W, again that implies something about pi. If W is irreducible, so then we have pi is surjective. So, now if both are irreducible, then pi must be an isomorphism. If both V and W are irreducible, so then this pi is an isomorphism. So, since we are working over with the complex numbers, so we will be able to say more than pi being isomorphism in the third case. So, in this case, so moreover, since we are working over algebraically closed field, so we can prove that there exists lambda in C such that this pi is going to be equal to lambda times identity on V if V equal to W. So, you assume both V and W are irreducible. So, that means V is irreducible and pi is an endomorphism from V to V. So, then it is supposed to be multiple of identity. So, that means it is a scalar times identity. So, basically the third part of the third result can be written as follows. If you look at this, the endomorphism space on V, which are actually commute intertwining operators. So, then the dimension of this space is going to be exactly 1, because if there is a map that is actually there in endomorphism of V that commutes with the action of A, then the Schur's lemma guarantees that this phi is supposed to be multiple of the identity. So, that means we have a natural map from endomorphism of V which commutes with the action of A to this one dimensional space which is spanned by this identity map on V. So, where you just take phi and then send it to this lambda, maybe we call it lambda phi, and this defines an isomorphism. Okay, so let us prove Schur's lemma, which is indeed very easy. Okay, just follows from actually some observations about the kernel and image. So, let us prove the first statement. So, if V is irreducible, let us recall pi is a map from V to W. So, if V is irreducible, so then we can see that the kernel pi is supposed to be subrepresentation of V. So, this is subrepresentation of V. Suppose pi is not injective, so we actually take pi to be non-zero map. Okay. So, this is a non-zero map. No, it can be 0 also, because lambda could be 0. So, let us not put any assumption on pi. Maybe we can assume that the respective modules. So, once we say that something is irreducible, it is already non-zero. So, we do not need to worry about it. Okay. So, we have this kernel pi, that is indeed a subrepresentation of capital V. Now, suppose kernel pi is actually non-zero, then that would imply that kernel pi is equal to V. So, that means pi becomes 0 map. So, okay. So, that means I can maybe let me just rewrite. So, what is the conclusion that we are making? So, if kernel pi is non-zero, so then since kernel pi is being subrepresentation of V, then we immediately get V is equal to kernel pi, and that would imply that pi is identically 0. Okay. But we do not want this. So maybe we can actually rewrite the conclusion as follows: either pi is 0 or injective, then pi is 0 map or injective map. Okay. Similarly, we will rewrite the second statement as well, it is okay. So, now if pi is non-zero, so that immediately forces that the kernel pi is 0. So, that means pi is injective. Okay. So, now let us move to the proof of 2. Again we have the pi from V to W. So, now we are assuming that W is irreducible. So, if we assume W is irreducible, then we can look at image of pi, which is a subrepresentation of W. So, this is subrepresentation. Now, the W being irreducible, that implies that either image is either 0 or it is full. So, in that case we immediately get either pi is 0 map or pi is surjective. Again I will rewrite the original statement: either pi is surjective or 0 map. So, now if both are irreducible and pi is non-zero map, so then we can conclude that pi is an isomorphism, because if both are irreducible and pi is non-zero map, then both pi, so pi is both injective and surjective. So, that implies that it must be an isomorphism. But we are working over with complex numbers. So, we want to actually conclude more about the map pi. So, let us actually see what we can do about it. So, here is proof of 3. So, pi is already an isomorphism from V to W. Since pi is a non-zero map, so we assume that W is same as V. So, in particularly, we will have an eigenvalue for pi. So, this is an endomorphism of V. So, pi has an eigenvalue, in particularly an eigenvector. So, there exists non-zero vector V in capital V such that pi of V becomes lambda. Now, note that if we take this pi minus lambda identity, so this is again there in endomorphism of V, which are actually commuting with the action of capital A. So, you have this pi minus lambda identity is in NAV. So, now from this pi of V being equal to lambda V, it is clear that the vector V is in the kernel of pi minus lambda identity V. So, that means the kernel of this map is non-zero. So, that would imply that immediately the kernel of pi minus lambda identity V is supposed to be exactly equal to V. So, this means the map pi should be equal to lambda times identity. So, there is no other option. So, this proves that the set of homomorphisms that commutes with the action of A. So, that can have exactly dimension 1. Now, it is also clear that okay, so this we can write it as a corollary. If A is commutative, that means the multiplication is commutative. So, then every irreducible representation of A must be one dimensional. So, let us write this as corollary. So, if A is commutative, so then any irreducible representation of A must be one dimensional. Okay, why this follows from the Schur's lemma? So, we basically use the last fact that any isomorphism on V will be scalar times identity. So, here so let us actually fix an irreducible representation. So, this is irreducible plus finite dimensional. So, we assume always it is finite dimensional. Okay. Otherwise, we can't talk about the existence of eigenvalue. So, the representation that we started with, they are all finite dimensional representations. So, we take finite dimensional irreducible representation of capital A, and we know that A is commutative. We want to prove that this must be one dimensional. So, now we can actually take any A in capital A and then look at its action. Let us say V comma rho is the given representation. So, then from this A we have this rho A, which is a map from V to V. So, we are going to just prove that rho of A is indeed algebra of homomorphism of representation. So, for that we just check, start with any B. So, this is something you fix, let B to be any element of A. So, then we need to check that rho of A and rho of B that commutes. But if you compute rho of A, rho of B, that is going to be rho of AB, which is same as rho of BA, that is same as rho of B, rho of A. So, that means rho of A applied on B times V is going to be exactly B times rho of A V. Okay. So, that means this rho of A is indeed homomorphism of representations. So, now if it is non-zero map, then that would imply that this is supposed to be multiple of identity. So, if okay, anyway, even if it is 0, then it is going to be multiple of identity only. So, then we can easily see that using the Schur's lemma, there exists lambda A in C such that rho of A is given by lambda A identity on V. So, that means the maps that we have from A to endomorphism of V. So, these are all just scalar maps. A goes to lambda A times 1 V. So, now you can see that you can take any subspace of V and we can easily prove that that is indeed subrepresentation of capital V. So, we simply take a vector and then see. So, you take a vector. So, since V is irreducible, V must be non-zero. So, we can pick a non-zero vector from capital V and just consider this CV. So, we are going to claim this is a subrepresentation of capital V. Since V is irreducible, then that would immediately force that this V is equal to CV. Okay, why this is a subrepresentation? So, let us compute what happens to, so let us start with some B in A and then we want to compute BV, what happens to this? This is same as rho BV applied on V. So, this is exactly, so A is acting as lambda A times identity. So, this rho BV is exactly lambda BV. So, that means this BV is again element of CV. So, this tells you that the subspace spanned by this V is indeed subrepresentation of V. So, that force V equal to CV. So, basically what we used, like we use this very basic linear algebra result. If we have two commuting diagnosable operators, then their sums and products will be diagnosable. So, that is what used implicitly here. Anyway, so this is an immediate application of Schur's lemma. So, now from this you can easily conclude that if you take representation, irreducible representation of Cx, then they must be one dimensional. So, basically in a given representation, so some, yeah, we will discuss about complete reducibility maybe later. Okay, I will stop here and we can continue to discuss about complete reducibility and so on in the next class. Thank you.